And thank you for joining us for today's Engage session. My name is Amelia Hames, and I'm with the Office of Communications here at Goddard. So we will start with our panel discussion, followed by a Q&A. The mics are on either aisle, so you can line up behind them if you have a question. And I think that is all the housekeeping I have for you today. So I would like to introduce Stephanie Getty, Acting Director of Sciences and Exploration.
Thanks, everyone. Can you hear me okay? All right, super. Thank you, Amelia, for the introduction, and I want to offer a good afternoon to everyone here joining us at Goddard and everyone tuning in online. A special welcome to so many of our partners joining us in person today. I really love the format of networking and then sharing this Engage session with you. As Amelia mentioned, I'm Stephanie Getty. I am the Acting Director of Sciences and Exploration here at Goddard. And before we begin, I want to thank Amelia and the rest of the team in the Goddard Office of Communications for all the wonderful work they've done in organizing this Engage series. The series has provided an opportunity not only to spotlight our missions, but also to facilitate everyone's understanding of the science behind them by convening experts on this stage here. Today we'll be discussing a trio of missions slated to launch later this month, all of which will help to map the sun's influence on Earth and our solar system. So when we think about heliophysics, we often think about the sun, and of course it's much more than that. A large component of heliophysics also involves studying the resulting space and weather environment that has a multitude of impacts on Earth and on the rest of our solar system. In many cases, space weather can influence and even endanger spacecraft, astronauts, and technology on Earth. Here at Goddard, our space weather is more vital than ever, especially as we help to advance NASA's goals of returning astronauts to the moon by studying the space through which astronauts will travel, and much more. The next missions that will help further our understanding of space weather are the subject of our panel today. They are the Interstellar Mapping and Acceleration Probe, or IMAP. This mission will help researchers better understand the boundary of the heliosphere, which is a huge bubble created by the sun surrounding and protecting our solar system. The Carruthers Geocorona Observatory will capture light from Earth's geocorona, or the part of the outer atmosphere that emits ultraviolet light. And the Space Weather Follow-on Lagrange 1 mission from our colleagues at the National Oceanic and Atmospheric Administration. This mission will use a suite of instruments to make real-time measurements of the solar wind, thermal plasma, and the magnetic field. We're fortunate to have some esteemed subject matter experts here today to discuss all three of these missions. First, our moderator will be Antti Pulkkinen, who is the Director of Heliophysics here at Goddard. He has led our heliophysics operations since 2021. Many already know that he'll be soon departing us for California to take on a 12-month detail as Director of the NASA Office of JPL Management and Oversight. Maryland is doing a pretty good impression of California right now, but we know that the Maryland winter is not so forgiving, so good timing. We are really happy for you, Auntie, but your job here isn't done yet, and that includes leading the panel today. Thank you. Shri Kanakal is the IMAP mission scientist here at Goddard. Alex Glosser is the mission scientist for Carruthers here at Goddard as well. And Dimitris Vassiliadis, I did it well earlier. Vassiliadis is the SWFO scientist over at NOAA. It is a pleasure to have them all here today. So without further delay, let's get the discussion going. Afterward, as mentioned, there will be an opportunity for in-person questions to extend the conversation. And thank you again for joining us. I'll turn it over to Auntie to kick off the panel.
Want to hear me? Okay. All right, well, thank you very much, Stephanie, and good afternoon, everybody. All right, just check. Again, my name is Antti Pulkkinen. I'm the director for Heliophysics Science Division here at NASA Goddard Space Flight Center. I will be in this position 1.5 day more. Leaving for JPL for this 12-month detail. No, actually on Sunday, but I'm really looking forward kind of finishing the gig here, partly as moderator of this panel. So really a pleasure and honor to be here today. So today we will be talking about the trio of missions, IMAP, Carruthers, and SWFO-L1. And really this is under the idea of space weather. We know that space weather is a hazard to our infrastructure in space and on the ground, and also hazard to humans in space, including to humans that will be taking us back to the lunar environment, and ultimately making the transit to other planetary environments such as Mars. On the NASA side, the Carruthers and IMAP will be addressing the key scientific questions pertaining to space weather. They have promise for transformational breakthrough scientific discoveries that will allow us to improve our understanding of the space weather and the hazards that it poses to us. And then, of course, on our partner NOAA side, the SWFO-L1 in turn will be providing breakthrough operational space weather observing capabilities. And then one of the things why I'm so excited about this trio of missions is that it really demonstrates this kind of a research to operations synergy that we have in our enterprise in heliophysics and space weather. In this case, the trio is sharing the same launch. Later this month, making the transit to Lagrange 1 point, where they will be making their observations. Again, really kind of underlining the full spectrum of things that takes place in our enterprise, from the research flow of information and capabilities to our operational partners to make sure that the nation is prepared for space weather storms and has mitigation strategies against the fury of the sun, if you will. Okay. So the logistics for here us today is as follows. With the powers of the moderator here, I will be warming up the panel for you guys with a couple questions, and after each panelist have had an opportunity to respond to those questions, we will be going to questions and answers part of the discussion here. So I'm really hoping that we will have a lively engagement with the audience here, and then we'll also taking some online questions. So that's the plan for today. We have another 50 minutes for the discussion, so I really look forward to that conversation with the audience here today. But let's get going with the kind of the initial remarks here. So the first question to all of our distinguished panelists is to talk maybe a little bit more about the mission itself. What is the mission all about, and why it matters? Why should we ultimately really care? And we'll start with Sri here talking a little bit more about IMAP.
Hello. Yeah. Yeah. Thanks for the introduction, Antti. I will try to keep a high-level overview of the IMAP mission. The IMAP mission is a long time in coming, from the decadal survey onwards, about at least 10 years, maybe longer than that. People were proposing to explore the two fundamental questions that we posed in the heliosphere. That is, how are the particles, energized particles that are emitted from the sun, how do they attain these high energies? And of course, as Antti mentioned, this has a direct bearing to space weather because these constitute a radiation hazard, both to spacecraft and to astronauts, particularly in the event that the NASA goal of going to the moon and then to Mars. So during the transit, astronauts will be affected by intense radiation, and we want most of it is particulate. And these energized particles can have damaging effects both on hardware and people. So that's one goal that IMAP will address. And the second one is, and we live in as Stephanie mentioned, the whole solar system is in a sort of a bubble. Just like an analogy would be the Earth's magnetosphere. As the solar wind blows and continues to move outward, it encounters local galactic matter in our Milky Way. So there is a sort of a standoff between the solar wind blowing outwards and the local, what we call the local interstellar matter coming inwards. And that standoff creates a sort of a shield, a bubble, in which the entire solar system is enclosed. And one of the things that this bubble does is to deflect very high energy galactic cosmic rays and essentially makes the solar system sort of habitable. And a new thing that was sort of discovered within the past, and I should say that IMAP is a follow-on mission to IBEX, which discovered some really hitherto unexpected features of our heliosphere. And IMAP was created to better these measurements and to understand what's really going on. And what's really going on is that it was found that the interstellar matter, particles and neutrals streaming in from outside the solar system, actually have, even though they are not as dense as the solar wind itself compared to that, they have a significant effect on how the entire heliosphere behaves, including the particle acceleration. So these two are very intimately connected, and IMAP will be the first mission to sort of holistically approach these two problems. It has a suite of 10 instruments, and with improved and enhanced resolution, both temporally and in energy, and with the suite completely cross-calibrated so that we'll have an absolute understanding of the various particle environments that the heliosphere is immersed in. For example, there are neutral particles streaming in from our galaxy. And it was thought that, okay, they will be coming in towards us from every direction. But the precursor mission, IBEX, discovered that there is an unexpected, nobody had predicted this, a band of particles that almost surrounds the heliosphere. And it's over and above particles coming in from everywhere. So this was completely unexpected. And IMAP will try to probe and understand the dynamics of this. And these kind of particle distributions have affect the energization that comes locally. And from the Lagrange 1 point, where we will be, the mission will measure not only these distant regions at the very edge of the heliosphere and how it affects us locally here, and also the particles coming in from the sun, which, as we know, there are many transient events like big ejections from the sun, like coronal mass ejections and so forth. And these actually act to locally accelerate particles. And some of the seed populations for that comes from the local interstellar matter. So they're very interchanged, connected things. And with these kinds of phenomena happening, and to come back to the space, so these, apart from this exciting science that we can do to discover our home where we live in, the entire solar system, we also learn, we get valuable knowledge about things that can actually affect us, not in a good way, like, for example, as I mentioned, radiation hazards to astronauts for the Moon to Mars traversal. And on Earth, for example, these solar events can affect even power lines, induced, what are called globally induced currents. All these will have certainly negative effects, and it would be nice to know if we can predict it and operationalize the science. That would be very beneficial. So in a nutshell, that's what IMAP is going to do.
Thank you very much, Sri. So the same question to Alex, and maybe Alex, you could elaborate a little bit about the name Carruthers itself as well.
All right. Well, thank you, Antti, and thanks everyone for coming out here today. It's really a pleasure to be part of this panel to tell you about, one of these 3 missions that's going to L1. So I'm going to tell you a little bit about the Carruthers Geocorona Observatory, or Carruthers for short. Carruthers is a mission that's going to explore Earth's exosphere. It's going to answer some fundamental questions about the exosphere. Basically, it's going to look at, the size of the exosphere, the variations of the exosphere, what drives those variations. And this is really the first time NASA's had a dedicated mission to do those things. So for those of you who aren't familiar, the exosphere refers to the outermost layer of Earth's atmosphere. It's where the energy from the sun first encounters the atmosphere of the Earth. Now, we often think of the transition between the atmosphere and space as being this very sharp boundary, where at one altitude you have atmosphere and the next altitude you have space. But it's not really like that. The transition is really much more gradual, and the atmosphere transition to space happens over not a sharp boundary, but over tens of thousands of kilometers. It's really very extended out into space. So just to give you an idea of how large it is, you can think of, well, what was the first time we observed it? And this was actually observed originally from the moon in 1972 as part of the Apollo 16 mission. So the person who designed and built that telescope was George Carruthers. He was outstanding NASA scientist and engineer, and he was particularly well known for designing this telescope that took the first image of the exosphere from the surface of the moon. Now, to give you a feeling for just how large the exosphere is, they couldn't even fit the whole image into that, or the whole exosphere into that image, even being at the moon. You really have to get further back. So Carruthers is going to build on this legacy by going further back, right? It's going to image the exosphere from L1 continuously, where you can really see the whole expanse of the exosphere.
And then there's the Apollo 16 image of the
Oh, that's
exosphere.
great. That's the first ever image. So what you're looking at there is the geocoronal glow. So the sunlight that's coming in from, the UV light that's coming from the sun is scattering off of the hydrogen in the exosphere and making this glow, which is what we're going to use to remotely detect the exosphere. So that's the science of Carruthers in a nutshell. The only other thing I'll tell you about, and we'll talk more throughout this panel, but this mission is really, really great team, led by the PI is Laura Waldrop at University of Illinois, Urbana-Champaign. There's, great program management at Berkeley, and, really a great team to work with. In terms of the space weather impacts, you might say, well, why do we want to study the exosphere? The exosphere is, it's composed of neutral particles, but it really modulates the space weather impact of a geomagnetic storm. There's a lot of buildup of energy in the inner part of the magnetosphere. That's the part of the magnetosphere that's very close to Earth. You get a lot of trapped energetic charged particles. Those trapped energetic charged particles interact with the exosphere and get lost to space as they become neutral. And so the exosphere really acts as sort of a thermostat on the energy, controlling the energy buildup and the intensity of the geomagnetic storms. So, by reducing the energy of those storms, you're changing the amount of ground-induced currents that can be carried in power lines. You're changing the amount of charging that can happen in satellites in this environment. It's really, an important part of the space weather puzzle.
Thank you, Alex. Dimitris, SWFO-L1.
Yeah, good afternoon, everyone, and thank you for the opportunity to talk to you about this new mission, SWFO-L1, that we have developed in NOAA alongside with our NASA partners here. So the two messages I'd like for you to carry when you think about SWFO are that it's a multimodal and mission with an immediate return of data. That's the meaning of operational. It's multimodal in the sense that it will be monitoring the sun's corona, so that would be the outer atmospheric layer. At the same time, it would measure the flux of particles that are coming continuously from the sun, both in terms of the plasma, the solar wind, as well as the magnetic field it carries, and also the suprathermal particles that are higher in energy than the plasma population. So in that sense, it brings us several different modes of information that are coming ultimately from the sun. The second major ingredient is this operational nature, which means that these data are streamed in near real time to users on the ground with a delay that's less than 5 minutes according to requirements, but in practice it is much less, closer to 3 minutes for time series data. For images, that latency is nominally 30 minutes, but in practice it's closer to 20 minutes. So within that short amount of time, we'll have data that are measured at a faraway point in space, Lagrange 1 that we heard about, 1 million miles from Earth, and then appearing on forecaster screens and on user tools within a very short amount of time. That's an incredible benefit for us, both in terms of forecasting and also for direct usage of the data. But that will not be the only type of application there. So to think in terms of meteorological analogy, you could think, for example, in terms of a monitor which would monitor a tornado or a hurricane in terms of atmospheric disturbance. At the same time, it would be measuring the real-time precipitation of particles, of rain or of hail particles, and also measuring the electromagnetic effects of these disturbances. So this would be a combined platform that would measure weather in several manifestations. In addition, in terms of who would benefit from this mission, there are numerous groups here in Goddard that would have direct applications for this, and I would be thinking directly of the heliophysics groups, for example. I would be thinking, for example, of Dave IBEX and Hugh O'Connor's hot flow anomaly studies in terms of the solar wind impacts on the magnetosheath, the Coordinated Community Modeling Center, CCMC, and the Moon to Mars would be a direct beneficiary of these measurements, both in terms of coronal images and also of solar wind measurements. Then there are specific groups that would be using the images for flow tracking, such as the Catholic University group led by Vadim Uritsky. So there is a whole host of applications that would be relevant here in Goddard, and also, of course, indicative of other groups elsewhere in the community. I would also say that this mission is presented as a NOAA mission, but it's really it relies on a very strong collaboration between the two agencies. NASA has provided not only acquisition help, but also they provided technical and managerial oversight in several instances. The linkage to the launch vehicle, the selection of instruments that have been provided by the University of California, Berkeley, University of New Hampshire, and SWRI, Southwest Research Institute. All these would be not be possible if it were not for the critical oversight and management that NASA Goddard, especially Code 400, has provided. So that relation to the center is a critical one, and we appreciate the collaboration through the last several years. With that, I would like to give it back to Antti. Thank you.
All right, thank you, Dimitris. All right, and I'll ask one more question here, but here in the audience, if you are wanting to ask question, please, you can start lining up behind the microphones. We're streaming this, so let's make sure that online audience hears the question as well. And if we don't get volunteers, I will volunteer. I'll just point people in the audience. I'm looking at Frank Coleman there in the middle. Your pick, but yeah. So if you don't mind, lining up behind the microphones. So let's put kind of a little bit of a more human side to this as well. So I might be very kind of curious to hear, let's in like a minute or two, a little bit about your background, your research background, and what you all have been working on, and then how that connects to the role that you all are playing in these wonderful missions. So maybe sure you can start.
So my career has really involved a couple of things, mainly centered around high energy particle detection, building instruments, understanding the energetic particle environment, both close to Earth and the solar origin particles. Like, for example, I was involved in designing an instrument called the relativistic electron-proton telescope, which flew on Van Allen probes. I led the instrument build of an instrument called MERIT for the Artemis program, Lunar Gateway Hermes. And now I'm involved as a mission scientist, looking at various energetic particle phenomena, their sources, their transport, and essentially their effects as well from the space weather point of view on human efforts, hardware, and that sort of stuff.
Okay, thank you, Sri. Alex, do you mind elaborating?
Yeah, sure. So my background is very heavy on the theory and modeling side of things and developing models of the nearer space environment. And one of the big missing pieces in those models is density in the exosphere. We need it for when we're trying to model the transport of gas from the upper atmosphere into nearer space. And we need it also when we're trying to understand the loss of ring current and other energetic particles in the inner magnetosphere. So from just understanding how the environment works, that got me very excited about the Carruthers mission. The other reason I'm excited is we have another project here at Goddard called STORY, which is actually measuring that charge exchange decay. It was proposed separately from Carruthers. It's independent, but they happen to be flying at the same time. Their prime missions are going to overlap. And so having this synergy, for me personally, got me very excited. So, basically, it's a great missing piece, that we're going to have now. And yeah.
All right. Thank you, Alex. Dimitris.
My background in space science has to do directly with the solar-wind magnetosphere interaction. So I've worked for several years, actually here in Goddard, on that, starting with studies between solar-wind interactions and geomagnetic effects, measured, for example, in terms of geomagnetic indices, individual disturbances at magnetometers, or ULF waves. And these are just some of the manifestations that show how the pathways of energy from the interplanetary medium to the Earth, to the ionosphere, to the ground, and so on, are captured in our models and so on. So I'm very sensitive to the efforts here at, for example, the Community Coordinated Modeling Center and elsewhere to capture that complexity as we've, of course, advanced in science. In the second part of my work, I collaborated on radiation belt research, coincidentally with Sri and his SAMBEX team and many others, to identify similar pathways now for the inner magnetosphere, not just for the global impact that translates into ground effects, but also into radiation belt and also ring current effects, and develop predictive models. Again, very sensitive to the applications of space weather. And here I would like to point out that this work that SWFO is poised to enable is really, again, pointing to the connections with Goddard, is really harking back to the work that was developed here in Goddard in the heliospheric science group, when it was still code 690 and where it was still in building 2, where several prominent theorists and experimentalists in solar wind, Melvin Goldstein, working with Bill Matthews of Delaware, of course, back then, Fitzenreiter, Klimas, Adolfo Viñas, and others put really their stamp on heliospheric effects, understanding the complexity of the solar wind as a system. And now we're going further back. We're starting to understand with missions like SWFO-L1, IMAP, PUNCH, the connection of the interplanetary medium to the outer corona. These are goals that we want that the community is attempting to fulfill, so that we can put together the links in that chain. So back then, we're just identifying pieces of that chain, but now we can see the whole edifice there. So back to you, Andy.
All right, thank you, Dimitris. Let's go to the audience. Sir, you would like to be the first one to ask a question?
So, Alex, you mentioned a little bit about synergy between other missions there, and any eyeball sensor detector we put out there gives us, more data and lets us build a more comprehensive view. However, I'm curious if the panelists are excited about specific, like, oh, our instrument or our observatory is going to work really well with this one over here, and this is finally going to give me the second perspective. Are you all especially excited about any synergies, either instrument to instrument or observatory to observatory, that naturally dovetail with y'all's work?
Great question. Who wants to go first? Alex, why don't we start with you? Switch it up a little bit.
Yeah, sure. That's a great question. A lot of times, missions are great individually. They're proposed individually with their own science objectives. They have their own, operational objectives in some cases. But a lot of times they work better together, right? And we talk about, in heliophysics, we don't just talk about a single mission. A lot of times we talk about the heliophysics observatory, suite of observatories. And, there's a lot of examples of how these missions build off of each other. In the case of Carruthers, of course, we want the L1 data, the space weather data that's coming in, because that's going to give us context for when we see these responses in the exosphere, what was driving them from the sun, right? What was the energy input upstream that's coming in and driving those dynamics in the exosphere? I mentioned earlier about the synergy with the STORY project. STORY is an ISS-hosted payload that we built here at Goddard that's going to launch next year, and it's going to look at the charge exchange decay of the ring current as it interacts with the exosphere. So being able to have the Carruthers data at the same time as we have those other measurements is really going to be outstanding. So, I guess maybe I'll wrap up and let other people share their thoughts, but I think the short answer is these missions really work better together than they work in isolation.
Dimitris, you mind elaborating your thoughts on the synergies there?
Many synergies that can be pointed to, and there's a very close synergy with IMAP that I will point to in a moment. But first, let me take the opportunity to point out that taken individually, these missions are, of course, important in their own right. But taken together, they really run the gamut for NASA, showing what the connections are, starting from the stars, starting from the interstellar medium and the interaction between our heliospheric bubble and other parts of the galaxy. They start there with ENA measurements that are available from IMAP. They go over to the solar wind environment. Then we look at the solar source of this with the outer corona that we image with our coronagraph, CCOR2, on board of SWFO-L1. And then we go right back at the interaction between sun and the planet, in this case Earth, and we reach down to the atmosphere of the planet. So it really is a continuum of interactions that really maps very well the capabilities of astrophysical, solar and planetary capabilities for the agency, for NASA in particular. Now, operationally, of course, there is a very close connection between the data streams that SWFO-L1 will provide, which will be the primary for the Space Weather Prediction Center out in Boulder, our primary customer for this mission, and also others similar to that here at M2M and also overseas, and the backup capability that IMAP will provide with its so-called iAlert or real-time beacon data. This is a very capable, very advanced set of measurements which are enhancing our capability to provide a snapshot of what happens in the solar wind and interplanetary measurement. And those measurements can be used interchangeably. So when one is missing, the other one can be used in its place. Or more creatively, they can be used in tandem, and we can create a more composite portrait from both of these missions, as well as ACE and wind, while they're still operational, of how complex the solar wind input that drives the magnetosphere drives its global models. So back to...
Very good. Thanks, Dimitris. Sri, any thoughts?
Yeah, Dimitris already covered much of that overlap. When missions are designed, we tend to focus on a certain set of objectives. You have to keep things together. You can't just say, I'll do everything, obviously. And given that, when there are other missions, you'll see that they come with a different perspective. But when the two perspectives match, there will definitely be an overlap, like with SWFO, for example. They will do the solar wind and the lower energy part, and IMAP, for example, to give only one specific aspect of this, is we'll do the resulting energized particles, like MEV relativistic energies. So they sort of mesh together. And within the IMAP mission itself, we are trying to do what may be called as an observatory holistic approach, rather than taking, okay, I have this instrument that does that, and then there's another instrument that does something else, and we write papers on what each instrument does. But IMAP from the get-go is interested in, and we have software capabilities to combine all of those various instruments. And certainly, not just within the mission itself, but we will also use data from other missions, such as SWFO, such as ACE Wind, and so forth. And our precursor mission, IBEX, for a very simple thing, like take one very particular aspect, like, for example, cross-calibration. We calibrate instruments on ground, but when they are in space, it's a totally different environment. So there's already, for example, IBEX flying out there, and we will measure, like, let's say, the energetic neutral atom streaming from the local interstellar matter, local galaxy, as IBEX does something similar. IMAP does much better, of course, with a high resolution, higher energy range, higher spatial coverage. But we can use that to calibrate at the overlapping regions of, let's say, particle energies. We can say, okay, these match, so we are in good shape. That would be a very technical kind of synergy with other missions.
I mean, maybe I'll kind of elaborate on this as well. I love the question. I think that's a critical insight into the nature of heliophysics and space weather. It's a system of systems where to be able to understand and predict the system, you have to understand vast range of spatial and temporal scales, a lot of complex coupled physical systems. My pet research has always been on the geomagnetically induced currents, or GICs, that Sri mentioned, that flow on the high voltage power transmission systems. And over the years, and I've been doing that work now almost 3 solar cycles. I know, hopefully folks know how long the solar cycle is. There'll be a quiz afterwards. It's about 11 years per cycle. And looking at those GIZ observations from transmission systems, I know you have fluctuations at the kind of a millihertz range, and understanding and realizing that all those fluctuations and those blips carry information throughout the entire Earth system. It carries information about the processes operating in the solar convection zone that pump mass, energy, and momentum into the solar atmosphere. It carries information about the processes that trigger the release of that mass, energy, and momentum in the solar atmosphere. Those blips carry information about the transport of that mass, energy, and momentum throughout the entire heliosphere. Those blips carry information about the interaction between these flows coming from the sun and the Earth's exosphere, Earth's magnetosphere, and Earth's upper atmosphere. And it carries information about the interaction between those processes in the magnetosphere and Earth's upper atmosphere and the upper mantle of the Earth. You know, you're getting all the way to the kind of geological considerations here. And you will have a signal of all those processes in those blips. So if that's not system of systems, what is system of systems, right? So the fundamental challenge for us here is that in order to truly understand the physics of the system and ultimately understand the level of hazard and then ultimately predict the system, you need to be able to observe, understand, model, and predict each and every section of that system of systems. So to me, the question about the synergies between different missions and synergies between the heliophysics systems observatory is absolutely critical point. Let's go to the next question there.
All three are being launched together. Was that always the plan for these three missions? And if not, has that provided significant cost savings for NASA and NOAA?
Who wants to take that?
I'm not sure I'm the best person to answer that, but I'll take a crack at it. Certainly, there is a definite cost savings achieved because they're all going to the same place. And I believe this was a part of it happened, part of it is happenstance, part of it was a coordinated effort to ensure that the three could be launched together. I don't know the details from the SWFO side or the Carruthers side. Maybe they can, maybe Alex and Dimitris can elaborate. Certainly, I believe the total cost is, for the launch is about 100 million. And to get three birds up there for the same cost, I think is a significant cost savings.
Yeah, they're like, you know, a lot of the big launches, they have excess capacity available. And, for us to be able to utilize that excess capacity to reduce the launch costs for, these ride shares, I think that's a kind of a transformational concept that we definitely want to utilize now and then also moving forward. Anybody else,
I can add some detail on that. So for NOAA, this was critical, a critical decision to take because, as a reminder of what SWFO is, it is the replacement of Discover, which is a NOAA inherent capability, and also of the operational aspects of ACE and SOHO. And the additional cost of providing the launch vehicle would be a significant consideration there. So finding the right rideshare partner and actually sharing that with IMAP, which is so similar in terms of science. Of course, it's not exactly the same in terms of operational priorities, but still overlapping in science goals, similar orbit, similar other priorities was an excellent match. And to have that added on by Carruthers, that's even better sort of decision planning. So the part of ride sharing with IMAP was decided very early on. And that was a significant boost in the operational capability that's enabled now.
Okay, thanks, Dimitris. Do we have any online questions, Miles? Okay, all right. Do you have the mic?
So this question's for Shri. I'm curious if you could say a little more specifically about how IMAP's capabilities compare to what IBEX can do. If you could just map that a little bit more.
Okay, that's a good question. IBEX is a much smaller mission. It has only two instruments. That's IBEX low and IBEX high. And they are oriented towards measuring this ENAs, the energetic neutral atoms that come in, stream in from the interstellar space. IMAP has two instruments, IMAP low, IMAP high, which are direct, which trace their heritage directly to the IBEX low and IBEX high. With the, however, the capabilities of IMAP low and IMAP high are ranging, depending on the type of the measurements, are at least 3 to 50 times better. They also measure this ENAs with and the sweep they do of the whole sky is also at a higher cadence. So what they can do, so one of the big discoveries, like I mentioned about IBEX, was this belt of particles, the so-called ribbon that surrounds the heliosphere. You would naively think everything comes from every direction. And that was a big major surprise, why you see a belt, not preponderance of particles in one small region. There are many theories about that, and it's still not settled as to what the origin and what's the explanation for this. What IMAP instruments do is they provide a much more comprehensive picture across particle energies, as well as at a higher cadence. But this so-called ribbon is not a static thing. It's evolving. It's evolving, and its evolution is a direct measure of how the heliosphere itself reacts with the local galaxy. So the temporal cadence with which these changes can be measured would tell us, for example, how the solar system is interacting. It's like saying, okay, you know, you're driving a car from A to B and your average speed is 50 miles per hour, but maybe sometimes you sped up, maybe sometimes you stopped because of a light. That kind of a thing, it's a complete different, much more detailed perspective. It's not just, okay, on the average, I went from Greenbelt to Bethesda or something like that, and maybe you got stuck on the beltway for 15 minutes or something. So those kinds of evolutionary things, IMAP is capable of doing much better than IBEX. Plus, there is a whole slew of other instruments, 8 other instruments. So it provides in a nutshell, it provides a big picture of the whole solar system, including as I mentioned, the important space weather aspect of how particles are energized. We know for the first time, that particles coming in from the local galaxy, what we call the local interstellar matter, even though that's much less tenuous than particles coming in from, let's say, in a very energetic CME type event. But these provide seed population, they affect the transport. The whole thing has to be studied holistically. And that's what IMAP does much better than, it's a complete game changer over IBEX, I would say.
All right, thank you, Shri. Do we have another question? Please.
Yes, I'll go again. So you all have clearly spent a lot of time doing this as people who have spent maybe inadvisable amounts of time staring at the sun. You care about this. What are you excited about? Unburdened by program requirements or talking points, what are you as individuals like really super stoked about seeing once we turn these spacecraft on and get them out into space?
Great question. Dimitris, you mind sharing first?
Thank you. Really good question. One, I'll point out to just 2 parts, but there are many others. So the single most important question that has to do with observations from L1, from Lagrange 1, of the solar wind and of the magnetic field that it carries, and also particle populations, is the complexity of the background solar wind and the structures many of which are geoeffective. That is, they produce space weather on Earth and other effects. So that is that leads to a series of questions that we've, of course, that the community has started addressing over decades now, but they've still not reached the final answer. And part of that has to do with the fact that the solar wind and other plasmas have this set of properties of self-similarity, for example, that the deeper you look, the more structure you uncover, something that Antti was referring to, that small details can actually make big differences, especially for predictive purposes, especially with the performance of models, for example. However, having more than one sensors there, having more than one plasma sensors, for example, from IMAP and SWFO-L1, and ideally also from the legacy missions, and also magnetic field measurements at the same time, allows us to map this complex structure that's incessantly flowing towards Earth and understand better what its repercussions are. The other result that I'm looking forward to, this is something that I recently got from interactions with the solar community, with the coronal community, is the very important boundary, similar to what Alex was talking about the exosphere and space, the very important boundary between the outer corona, the edge of the solar atmosphere, and the solar wind, the adiabatic expansion of the corona into the solar wind. That has not been mapped yet. People sketch it as an ellipse or an ellipsoid, but in fact it's sort of a fractal. It's a frothy. People use expressions like frothy and turbulent to express how dynamic it is. And missions like SWFO may be able, with its with the SICOR-1 on GOES 19, that I didn't have time to refer to, but SICOR-2 can complement research missions such as PUNCH, for example, and other sort of triumph of NASA. So that would be two research goals that I would be looking forward in the next years for the results. Thank you.
All right, Alex, what are you really, really stoked about with Carruthers?
Well, with Carruthers, I think there's a lot to be excited about. And in particular, it's the first exosphere-focused mission. We only have a handful of images of the whole exosphere, very few. And we certainly don't have any from different vantage points or any from that are observing over time. So there's really some very fundamental questions that we just don't know right now. Like, we don't know what kind of structure there is in the exosphere, density structure. We don't know how it changes in time. We don't know how rapidly it might change in time. So there's a lot, when you look at something for the first time, when you do this type of exploration science, you're going to learn new things. And there's a lot of low-hanging fruit, just from these very basic questions. What's the structure? How is it changing in time? How is that different during geomagnetic storms versus just more of the day-to-day type of solar wind driving and solar input driving? So I'm just excited for just getting at those basic questions. I think that's very exciting personally.
Sri.
So perhaps it should be more or less obvious. I keep talking about this ribbon. So to me, that's one of the most exciting things that IMAP can do. Having said that, there are other things, which I haven't mentioned so far, which is IMAP also measures the composition of the local interstellar matter. For example, it's done with ratios of abundances of elements. So the ratio of, pick a couple of types of elements seen in emerging from solar eruptive events. The ratio of, let's say, neon to oxygen would be very different from the local interstellar composition to the solar composition. So knowing about those things can actually lead us to how stars synthesize these elements. Okay, so for example, deuterium, it's sort of almost primordial, goes back to, if I'm not mistaken, almost to the Big Bang. So some of these kinds of things are really exciting for me. The primary excitement for me is I really want to understand why that, so, for example, it's not like we are completely groping in the dark. We know there are possibilities as to why you see the ribbon. One of the possibilities is that, for example, particles are trapped in a small region controlled by the interstellar magnetic field direction, and resulting sort of turbulent waves there, which interact with the particles. They confine these particles, and therefore, when they are emitted, they're coming from a specific region, and this model is called spatial retention model or something like that. And that's okay. It sounds reasonable, but what is the physical evidence for that? It's not the only model in town. So I would like to really understand, for example, how this thing, and this was a completely unexpected discovery. And therefore, having said that, then maybe if when IMAP launches and when we start collecting data, it's entirely possible, or even quite probable, that we may see something that we have never seen before. And if some phenomenon were to happen, I would drop everything and go for that. So I'd like to keep my mind open, but if you ask me what is my personal preference now, the first thing is I'd like to understand why there is a ribbon, and the second thing is what's the local interstellar matter composition and what that tells us about space beyond our solar system.
Yeah, and I will tell, kind of a little more colloquial answer is that when we go to new places, look in a new ways with a new pair of eyes, new things, you will discover a lot of unexpected things. Like, and that's the true nature of discovery, right? You go to new places, you observe new things, and this is the promise of these science missions. And as I mentioned earlier on, I think also the research to operations and kind of the operational partner dimension is really exciting. It really is a true demonstration how this full pipeline from research to operational capability actually works. A lot of the observations that SWFO-L1 will be carrying out for the operational benefit of the nation were demonstrated first through NASA science missions. So it kind of closes the loop in that R2O sense. And if that's not powerful, what is? So I think that really speaks to my space with our heart. That this is how things are supposed to work. We're at the time. Time flies really fast. Hour goes by. Zoom like that. I'm hoping that we would have another hour here, but I know you guys need to go do other things. So we'll wrap up here. Thank you for the panelists again, and thank you for Stephanie coming here and for your opening remarks. So let's just give a round of applause. And good luck for the launch. Go IMAP, go Carruthers, and go SWFO-L1. Thanks, everybody.